I want to discuss two potential sources of error when making these measurements, these power measurements. One of them we've already looked at and touched on, and that is concerning the parasitic inductance we have sitting between the CSR probe tip and reference over here. So we've got this parasitic inductance here and this parasitic inductance over here. Mainly due to the leads on the CSR resistor. So essentially what we have is an inductor in series with the CSR resistor, and we're not getting a true picture of the current through the circuit, the real current, or real power, if you will, in the circuit when we're not measuring strictly just the resistive part of the CSR. So when we've got parasitic inductance involved in between the probes, we know that our readings are going to be incorrect. Now the second source of potential error in these circuits, is particularly when they're oscillating at high frequencies, is inductive pickup. And this is particularly a problem when we're using single-ended probes like we are, where you have this ground lead coming off the probe. And in this case, this is probably about a 4 or 5 inch ground lead, reference lead. So what's happening is we have an electric field set up, a varying electric field, changing electric field, along the CSR here in this direction, back and forth in this direction. And any wire that is parallel to this wire is going to have an EMF induced in it. So if you look at our ground lead, we actually do have part of the ground lead in parallel. Even though it's a few inches away, it's in parallel too. So that ground lead is going to have an EMF induced into it from the high frequency oscillations in the circuit. So that's going to give us an indication on the scope, and that's going to be used as part of the multiplication process to the battery voltage to give us our instantaneous power product. And that, of course, is going to be an erroneous measurement, because we are picking that up via induction. It's not a real current flowing through the circuit here. It's being picked up via induction. Okay. Now, to further illustrate this potential problem, I am just looping the CSR probe here onto itself. So it's just forming a simple loop. The coax comes through here. The ground does carry on at least to this point, but the center conductor goes all the way through to the tip, and then our ground lead comes all the way back this way. So it's essentially, we have a loop formed here, and it's because of that that this loop is able to have EMF induced in it. If this loop comes into alignment with any electric field, changing electric field, this loop will integrate that electric field and produce an EMF, and of course that EMF is going to be displayed on the scope. Okay, so let's hook up power here, and I'm just going to hold the probe close to myself here so it's not anywhere near the circuit, and you can see waveforms. The current trace is showing pretty much zero, the power is pretty well zero, and there's our battery voltage trace. So we know the circuit is working and oscillating. So now I'm going to move the current probe so that the ground lead is in parallel to our battery, one of our battery leads, like that. And look what's happened to our display. Our current probe is picking up quite a bit of voltage, It's on a 500 millivolts per division. So we got just under 1 division peak to peak of oscillation there. There's pretty well 0 DC current there. And you can have a look at the mean current. Again, it's close to 0 that this scope will give us, 2 or 3 millivolts. But there's a considerable amount of AC current on there. Okay, and now I'm just going to slowly move the probe away, and you'll see how it falls off. Okay, we can place it under the load resistor itself, like that. And again, we have some pickup. Move it away, bring it closer. Now I've got it beside the battery negative lead, and we could actually probably even put the probe in line, so it's essentially in parallel with the negative or positive battery lead here. And again, we have a good strong signal, about 1 division on the CSR probe. And just out of curiosity, what does our PBAT says? Our PBAT says 2.2 watts. That's interesting. That CSR is showing 0 current, so it should be pretty well 0 watts. But okay, let's try moving it to the battery negative side here again. That's interesting. Now it's showing a negative 1.2 watts. There's the display. Okay, and I can just move the probe close and far, and the amount of induction changes. And consequently, so does the mean power value change. So you can see this is definitely a potential for error, and I think that's why just moving the probe around like I was in my last video, I was getting a variance in the battery power. So to combat this, what I've done is I've soldered 2 pairs of wires across my CSR. One pair, the green and red, is right tight, soldered right tight to the body of the CSR, and the orange and yellow pair is about 1 inch or so on either side of the resistor to emulate our negative mean battery measurement. So then what I've done is I've haphazardly twisted this telephone wire pair together all the way down, and I will put the scope probes here, the scope probe, the CSR probe, to make a measurement on this end of the wire. So twisting it is going to help keep out in induced voltages, and having it far away from the circuit will also help prevent the ground lead from picking up any stray signals and giving us an erroneous measurement. So I'll just hook that up in a moment, and we'll have a look and see what our measurements are.